someday they're going to actually bring the wastebasket in here. I've been in this room for years. If you bring one in, they migrate out, but I don't think there's one back there. Anyway, if you have a transmission line, that's not good, Mark. No, I'm not going to ask him. I went and I brought a bunch of markers. Supposedly new. I'm having questions now. Anyway. All right, let me just, and this has a characteristic of impedance of Z0. So the first thing I'm going to say with this, understand that this is usually termed the load right here. I hope you can see, this is not the darkest marker. There's more down there, I may try. This might be a little bit, but it's got, the length of the line is L, the load is always put at Z equals 0, and the line has a length minus L. Now, really, what happens here is there's also some source resistance and some voltage source here, some Vs. Y'all follow me? That's really just a basic transmission line, where the transmission line is being used to conduct either power or communication information to some load. That's it in a nutshell. Just like an extension cord is used to take the wall voltage current and put it to some appliance. And we talk about this. One of the things we always do is find out how much electromagnetic, how much of the voltage, if it comes down and strikes this, will be reflected. And that's called the actual reflection coefficient. No matter what. So the reflection coefficient, the symbol is gamma sub L because it's the load. And that's always, and this is something you get used to hearing from me over and over again. When you think about the reflection coefficient, you always take the impedance you're going into, which would be the load, minus the impedance you're coming from, which in this case is the characteristic impedance of the line. You all follow me on that? And you divide it by the sum. Now last time I said, this particular value can have a maximum value of 1 and a minimum value of minus 1, but it can be imaginary. You all remember my rationale for that? Those are the two extremes of load. But it can have any value in terms of a real and imaginary part, but it's confined to its maximum being positive 1, its minimum being minus 1. That's it. That's the thing to keep in mind. Now that reflection coefficient is used because it's technically equal to the ratio of V0 minus over V0 plus. So it's a ratio of the reflected to the incident voltage waveform's magnitude. Are you with me, guys? Now we look at something. We look at anywhere on this line, you're going to have a voltage waveform. And I'm going to do this in the phasor map. So anywhere on that line, you'll have a voltage V of Z. And V of Z is equal to V0 plus times E, and here I'm going to do something because, well, I'll make it a more general thing where we can have a lossy line. E to the minus gamma Z plus V0 minus E to the gamma Z. So that's the equation for the line, or for the voltage on the line at any point Z. Do y'all follow me, class? And here I just restated what we developed in prior lectures. Now, here's where it becomes important to see. I know that V0 minus over V0 plus is gamma L, right? So gamma L V0 plus is V0 minus. Do y'all see that? So what I can do is this. I can simply put gamma L in there, and bracket those terms and bring V0 plus out. That's the way it's always done. Y'all follow me? Now we have the ratio reflected to transmitted, or I should say to incident and reflected voltage, gamma L, and then we have these exponential terms. Now, here's something important about this. When I look at these terms, maybe looking at that way, you won't really appreciate it. I'm going to do something, and you don't need to write this down yet. I'm just going to let gamma be strict real. Okay? I'm going to just get rid of the loss. The alpha term would just make it decay in magnitude. So if I did that, then I would have V of Z equal to V0 plus, and then it would be e to the minus j beta Z right here, and it would be plus gamma L e to the plus j beta Z. And I'm going to make a comment about this. Now, if you look at this right here, what this is this right here is nothing more than the magnitude of 1 rotating in an imaginary plane. E to the j anything, do y'all realize what I'm saying here? If you have something of length 1, and this is the angle theta right here, if this is the real axis, and this is the imaginary axis, then this can be thought of as just e to the j at this positive angle, j theta, right? Can y'all follow me on that? That's what e to the j represents. J is imaginary. The magnitude of this e to the j would always be just 1. It's exponential to a j something. That something is an angle. Do y'all follow me? So if it's e to the j 0, it's just got a value of 1. If it's e to the j pi over 2 or 90 degrees, it would have a value of just j, strict imaginary. Do y'all follow me? Then if it rotates this way, here, if it's e to the j pi or e to the j minus pi, it's minus 1, and so forth. That's the only thing e to the j anything does. Now the angle there, theta, is representing this beta z. Beta is radians per second, or radians per meter, z is in meters, so the combination will be radians. Y'all follow me? Now, when you think about these two terms, I know that gamma L has a magnitude and an angle as well. I'll put it here. It has some magnitude, gamma L, and it's e to the j, and call it the angle associated with gamma L. Follow me on this? I'm doing this for a very important reason, so you can appreciate the next step. Now, when I look at that right here, with that in mind, I have V0 plus, then I have this e to the minus j beta z plus gamma L, and then I can combine the exponents of the gamma and beta. So then I have e to the j beta z plus the phase angle associated with gamma L. Y'all follow me? The only thing I've done here is now I let gamma L, and I should put a magnitude here. Do that. With me? I'm going to see this, you understand? It's just making things a little easier to see what I'm about to do. Now, if I look at that, remember how I said these exponents rotate, right? We're going to talk about the minimum and maximum value that this can have, the voltage. Ready? Think about it. What would be the maximum value? And think in terms of rotation. Let me show you what I mean. For now, let's not even worry about V0. Let's just take a look at this term right here, where I have these two terms. Y'all agree that that first term right there, since that's a minus, that's something down here, and this angle, it would still have a magnitude of 1, but it would be at an angle of theta here would be beta z. Y'all follow me on that? This would be the real axis. This would be the imaginary axis. Y'all follow me? It would have a magnitude of 1. That represents this term right here. Now this term's a little different. This term has a magnitude of gamma L, doesn't it? Y'all follow me? and it's rotating in the opposite direction. So here, it's less than that. So this has a magnitude of gamma L, and this angle now is going to be, actually this should be minus beta Z, would be beta Z, let's go this way, plus the angle associated with reflection coefficient. Can you all appreciate that? Now I want you to think about this. Remember, that angle will change based on the value of Z. So I got two vectors that are rotating like this. You all see this, class? One's going positive, the other's going negative, and we're doing a summation of the two. Now, how many see at some point the two will overlap? How many see that? Right? And at some point they will subtract, right? Well, when they overlap, that would be the maximum possible voltage. Y'all follow me? And when they subtract, that would be the minimum possible voltage. And that's where the term standing wave ratio comes from. And I'm going to try to, I'm really looking for something here that rhymes. I've got some more down here. I think I'm lucky with one of these. So, I'll put that over here. No, I'll put it right here, actually. So now when we talk about the standing wave ratio, can you all hear me okay?
Yeah.
Is that picking up? Or do I?
No, you're good.
Okay. So the standing wave ratio, it's actually volt. Like, I feel like I've been punked. There's a show called Punked.
I think we know what you need to do.
I don't know what the world's going on.
We just gotta give him one. We got to. We gotta give him.
All right, I owe you this. Go ahead.
Hey.
What you're going to see here now is when you do this for the standing wave ratio, it's the volt.
Okay, come on.
It's you.
That's a prank. Here, I got it.
Another one?
Here's a black. I got black right here.
Yeah. Let me have that one in black.
My black one's right here.
There's two black ones. I think I gave you the wrong one.
Here's the black. Here's a good black one right here.
I got one. This is problem usually don't happen at this level. If I grade 5 markers, this is an audit. Is this good or junk?
No, that's good.
This is the one you used yesterday. So
This one?
Yeah.
Is this junk?
Shouldn't be.
Test him. Make sure you know which one's mine. I don't want his junk.
There was a bad one and a good one. I thought I threw the bad one away. Apparently not.
All those get carried. All right, so volting standing wave ratio, this is a good one. So this is V max possible on the line. That's for all values of Z over V min. And if you look at that, since I kind of made the point, the maximum value will be when these two are added, didn't I, class? And the minimum value would be these two are subtracted. Do y'all follow me? So the way it works is this. That's equal to simply 1 plus, and you got to put magnitude of gamma L here. That's as big as it gets over 1 minus gamma L. You all with me? So that's the ratio of the maximum to minimum voltage on the line. It's called the voltage standing wave ratio. It is also the current standing wave ratio. One is the other. So it's usually, a lot of times, just SWR. If you see standing wave ratio, that's what it means. Got it? Now think about the possible values. When I look here, think about gamma L. What's the maximum value gamma L can have? 1, right? You'll notice there's magnitudes of gamma L. So the minimum possible and the maximum possible have the same value if we take an absolute value. Do you all agree? So what are the values? If gamma L is 1, implying the reflected wave is the same as the incident wave in magnitude, look what happens. 1 plus 1 is 2, 1 minus 1 is 0. 2 over 0 is tending to infinity. You all follow me? So the standing wave ratio's peak value can be infinite. Do you all follow me on that? And remember that, SWR becomes a very, very important thing when you're designing anything to do with power amplification, antenna designs, because you want that as low as possible. Now, what's the minimum value? Well, if you think about this, if gamma L would be 0, nothing is reflected. You all agree with that? And that means the standing wave ratio should be 1. 1 plus 0 is 1, 1 minus 0 is 1, it is 1. That's the smallest possible value that the standing wave ratio can have. And reason it out with yourself. Now, why is that so important? Because when we have a power amplifier, and we're going to drive an antenna, this happening with person, you want that standing wave ratio to be as close to 1 as possible. I did a design, a very expensive design for an antenna, but I didn't do the assembly of the antenna. I did the fundamental design, and some electronics guys in another part of the country did the assembly, and we sent it out to Ball Aerospace to test in a very large anechoic chamber. And when he hooked it up with the main feed, he said, this has a SWR of 4. Now 4, if you're a design engineer, says you're a moron. I mean, you can't get any worse than that, basically. No power, the power coupling is horrible. So I knew this guy, and he was a real engineer. He was an electrical engineer, not a technician. He says, I'm gonna open it up and take a look. This is a fairly complicated antenna design. So the technician, this is at 1.4 gigahertz was the frequency. The technicians, remember, technicians are not engineers. They don't know all the science behind things. They know how to do basic. So had left a solder ball, I don't know, quarter of an ounce worth of solder or better on there. That acted as a huge inductor when current was flowing, and it caused this huge inductive reactance at that frequency, and therefore there was not impedance matched. Now the whole idea is, remember back to this gamma L, you want this thing to be 0 if you want a standing wave ratio of 1. Well, if gamma L isn't equal to the characteristic impedance, or I'm sorry, if ZL isn't equal to Z naught, and my input impedance was designed to be Z naught, it was for a 50 ohm drive, but it was like 100, and it was because of that solder ball. So that's a lesson about SWR that you could take to the bank and remember. Don't ever try to do something with power amplifiers if the SWR gets more than like 1.5, because you're blowing power back into the amplifier to blow it up. All right. That's my little story about this. Now, after that, next thing we do, you should be wearing a mask, but I've been told if you're drinking coffee, they didn't say how long between the drinks. Okay, next, what we're going to do now that we've cleared that up, we're going to talk about the input impedance to this line right here based on the formulas we developed. You're going to see that this gets to be interesting. I'm going to leave that line up. So what we're talking about is this. If we're looking right here, and we want the input impedance, Z in, to that line. Y'all follow me? Like if you cut that transmission line here, got rid of that thing, you want to figure out what the input impedance is. It's a ratio of voltage to current. Y'all agree with that? So what is it? Well, the input impedance to that line, when Z is equal to minus L, would be the equation you have for voltage, which you found out just a second ago was V0 plus. And here I'm going to do something, well, Whitworth does, I'll do it the way Whitworth does. So then you have E to the minus gamma, but I'm going to tell you one thing. You see how this is measured at 0 right here, and these are positive values. So if the line is length L, Z is actually minus L at this point. Y'all see that, class? Let's circle that. So that means this becomes e to the minus gamma minus L or plus L. And then it's going to be plus the reflection coefficient times e to the minus gamma L. All right, that's the voltage at any point in the line. Now I'm going to divide that by the current on any point of the line. Some of this we covered last time, and you might need to refresh yourself. But the equation for the current would be V0 plus over Z0. Y'all remember I can do that, right? And then comes your first coefficient, which would be e to the gamma L. And here it's going to be minus the reflection coefficient times e to the minus gamma L. Now the reason it's minus gamma L there is, remember, normally this was just I0 minus, right? But I0 minus is V0 minus over Z0, only there's a minus sign because it's going in the negative direction. And we can prove that again if you'd like. When I come down and do this, there's something that becomes real clear if you look at it. See how V0 cancels, top and bottom? Everybody okay? So I'm just going to go ahead and put Z0, which is the characteristic impedance of the line there. Now I'm going to make a statement that some of you remember hyperbolic functions from math, your mathematics courses? Hyperbolic cosh, hyperbolic tan. Does anybody remember them? I'm going to remember sine, cosine, stuff like that. Y'all remember that, right? Do you remember if you had, like, I'll just put this up. These are Euler's identities. If you had the sine of x, that was equal to e to the jx minus e to the minus jx over 2j. Do you remember that? That was one of three Euler's identities. How many do? Maybe it was theta, whatever. X is just the dummy variable. Y'all remember this? This is Euler's identity. Second identity was what? For cosine, right? Cosine of x was equal to what? E to the jx, right? And here it was plus e to the minus jx over 2. Y'all remember that? How many do? That was cosine. Then you remember that you had just e to the j, maybe I should use theta. E to the j theta was equal to cosine of theta plus j sine of theta. Do y'all remember those? All right, those are for functions where the argument of the sine is strict real. There are hyperbolic functions that are similar to this, and I'll put them here. One is sinh of x, that's just e to the x minus e to the minus x, right here, over 2. Then there's cosh of x, e to the x plus e to the minus x over 2. And then finally there's e to the x is equal to cosh of x plus sinh of x. I don't know if you remember those. Those are hyperbolic. You don't usually cover them at length at the undergrad level. But those are hyperbolic functions. The reason we don't is most of the time we just deal with exponentials. We don't bother writing them in terms of cosh or sinh. But you all see the similarities. There's sinh, hyperbolic, that's sine. The only difference is there's no imaginary component up there and there's no j downstairs. Y'all with me? Same deal here with cosh and with this expression. So I won't do this for the sake of time, but if I take this and I simply expand it, remember, I gotta say this too. These terms, x here can have a real and imaginary part. It can be magnitude and phase. It doesn't have to be just strict real. You all follow me? And you can actually prove if x is strict imaginary here, it will be the sine. And I'm not gonna do it right now. The definition of sine